Good morning. Today I'm going to talk about new results on the solution for a class of integral boundary value condition of Dille partial differential equation with fuzzy data with my supervisor Lele Sadia Shedli and my co-supervisor Saeed Miliani. This is the outline of my presentation. I will start with introduction, move on to preliminaries of my research. In session 3, I will talk about new results on solution for a class of integral boundary value condition of the Dille partial differential equation with fuzzy data. And finally, I will finish my work by the main conclusion and some future work. Well, for the introduction, I will compare classical set, fuzzy sets, and intuition set fuzzy sets. This is an example to compare classical set and fuzzy set. Consider an inverse set T, which stands for temperature, the cold temperature, the normal temperature, the hot temperature. They are all subsets of an inverse set T. We defined classical approach. For example, subset cold is the temperature between 5 degrees centigrade and 15 degrees centigrade. Similarly, we define normal and hot. The characteristic function of one of these subsets, for example, subset cold, is equal 1 if a temperature in subset cold, 0 if a temperature not in subset cold. One should notice that 14.9 degrees centigrade is cold, while 15.1 degrees centigrade is normal. Applying that, the classical set have a rigid boundaries. Because of this rigidity, the expression of the word or the expression of the data becomes very, very difficult. Because for me or anyone for us, we feel that very easy. 14.9 is cold, while 15.1 is normal. That is bizarre to have such an approach to categorize thinking value sets. In fuzzy, it's easy to present them here. How do I do it? Well, this is my temperature axis, and this is my membership group function. Now, how do I define that? If the temperature is around 10 degrees centigrade is cold. If the temperature is around 20 degrees centigrade is normal. If the temperature is around 30 degrees centigrade is hot. If I would like to choose another temperature, for example 25 or maybe 15, it can be here. It can be simultaneously normal and cold with membership grid 0.5. Well, 15 is below 2, both normal and cold. If I would like to choose another temperature, for example 22 maybe can here, is the temperature more likely belong to the subset normal, whereas I would like to choose another temperature, for example 28 maybe can here, is the temperature more likely belong to the subset hot. Well, this is a much nicer way to present a set. Well, this is how the imprecise data can be categorized in a much nicer way using fuzzy set theory. In classical set, we say only a member in a set. Here, we say a member in a set associated with membership grid function. This theory is introduced by the Professor Lotfi Zadeh in 1965. That is an extension of the classical notion. Here, a definition of fuzzy set defined by this formula, where this function is called the degree of membership equals 0 between 0 and 1 and equal 1. By contrast, the characteristic function only 0 or 1. Now move to make the difference between fuzzy set and intuition set fuzzy set. Let's consider this example. Let A be the set of all elective countries with elective government, with a note the degree of membership is corresponding for the electorate who have voted for the corresponding governments. By definition, always in fuzzy set theory, the degree of non-membership equal 1 minus the degree of membership is corresponding for the part of electorate who have voted outside of the government. In that sense, mean that fuzzy cannot give us more information or more data or in comprehensive way. Because the question here arises, how can we categorize the electors who have not voted at all or made a mistake in vote? We need to categorize this part of electorate. For this reason, or that's why the Professor Krasimir Atanasov add another degree, is the degree of uncertainty. In this case, if I choose the degree of non-membership is corresponding for here, the degree of non-membership is corresponding for the electorate who have voted outside of the government. Now we have the possibility to categorize the last part of electora, the electora who have not voted at all or made a mistake in vote and so on, by 1 minus the degree of membership minus the degree of membership. This theory is introduced by the Professor Krasimir Atanasov, which is generalized the deficit set theory, which is identified by membership function, non-membership function, and indeterminacy function. It's declared that the intuitionistic fuzzy set can be described the fuzzy character of thing more detailed and in comprehensive way in dealing with the vagueness than fuzzy set theory. For the preliminaries, I will be mainly talking about the tools I used in my research. This is here a definition of intuitionistic fuzzy set defined by these two functions, where these two functions is called the degree of membership and the degree of non-membership respectively. And always the addition between two degrees is between 0 and 1. And here a definition of the degree of non-uncertainty by 1 minus the degree of membership minus the degree of non-membership. And here we define the collection of intuitionistic fuzzy number is denoted by I of 1, and here defined by this formula, plus verify these 4 conditions. And here an example of intuitionistic fuzzy number is the triangular intuitionistic fuzzy number, where the following function called the degree of membership and the degree of non-membership respectively. And here we define the lower and upper alpha cuts of an intuitionistic fuzzy number by this formula. And here the extremity or the end point of the lower and upper alpha cuts of an intuitionistic fuzzy number in I of 1. And thanks to this alpha cut, we define the following operation, the addition and the multiplication by a real number. And here a definition of the difference between two intuitionistic fuzzy numbers is called the Hokahara difference if these exist in I of 1 and satisfy this equivalence. And on space I of 1 we define the following metric, where the metric space I of 1 the after is complete. This intuitionistic fuzzy metric space was first initiated in 2015 by Professor Saïd Miliani and our laboratory colleagues. And also we need this intuitionistic fuzzy metric space with the not the supreme white metric by this formula. And we can show that this metric space is a complete intuitionistic fuzzy complete metric space in I of 1. And this intuitionistic fuzzy metric space we will have relying on it in our common researches. Here a definition of integrably bounded function, and if we have a strongly measurable and integrably bounded function, automatically is integrable. And here a definition of the lower and upper alpha cut of the double integral of intuitionistic fuzzy function in I of 1 defined by these expansions. And here a definition of continuous function at point x0, y0 if satisfy these conditions. And in this slide, this definition is about the intuitionistic fuzzy partial derivative of an intuitionistic fuzzy function in I of 1. If we can compute these elements in I of 1, and these H differences exist, and this quantity is equal to this limit, in this case, this element is called the intuitionistic fuzzy partial derivative of the function f in I of 1. Move on. The aim of this presentation is to illustrate the existence and uniqueness result of a class of integrably boundary integral boundary value condition of partial delay differential equation with fuzzy data. This is our model, and here are our initial conditions, and here the ingredient of our equation. And here we define state-dependent delay by this formula. A solution for our model if can be continuous and satisfy this following equation, And for the existence and uniqueness result, we suppose that function f is continuous and satisfy the Lipschitz condition, If we can guarantee the existence of this condition or this hypothesis, in this case, our model has a unique intuition-seq fuzzy solution. To prove this result, it's clear that the solution of our model is a fixed point of the following operator defined here, and we will prove that this operator is a contraction operator, and by using Banach fixed point theorem, we can find a unique fixed point which is the intuition-seq fuzzy solution to our model. For this final slide is about the conclusion and the future work, where this work is about the delay partial differential equation with uncertainty for a class of integral boundary value problem. We are so far presented delay partial differential equation with uncertainty with the initial is an integrably bounded initial condition, and under sufficient condition we have proven the existence and uniqueness result of the solution related to this equation. And as a perspective, we would like to find some application related to this equation, and additional research focuses on the uncertainty delay partial differential equation with no local conditions. And thank you for your attention.
Hello everyone, I hope you are well. I would like to take this opportunity to present my work entitled Fuzzy Fractional Boundary Valued Problem. This work was realized in the Laboratory of Applied Mathematics and Scientific Computing under the direction of Mr. Saeed Miliani and Mohammed Al-Omari. This is the plan of our presentation. We will start with the short introduction. Then in the second section, we will define some definitions and theorems that will be used in the following. And in the last section, we will present our theorem concerning the existence and uniqueness of the solution. A boundary value problem is a differential equation together with a set of additional constraints called the boundary conditions. A solution to a boundary value problem is a solution to differential equation will also satisfy the boundary conditions. In 2001, Marty and al. Presented a criteria for the existence and uniqueness of solution to two-point boundary value problem associated with a second-order nonlinear fuzzy differential equation. And in 2008, Chen and al. Corrected the error of Marty and gave a necessary and sufficient condition to show the existence and uniqueness of such a problem. So from last paper, we inspired our work, but this time with the fractional calculus. In this section, we present some definition and we introduce the necessary notation. We denote by E1 the class of function defined in R into 0, 1 such that you satisfy the four property below. For all alpha in 0, 1, the alpha cut of an element of E1 is defined by this formula. By the previous property, we can write the alpha cut of U by this notation, where U is the left-hand endpoint of U alpha, and this is the right-hand endpoint of alpha cut of U. So by the extension principle of ZF, we can define the sum of two elements U and V of E1 and the multiplication by scalar. And the distance between two elements of E1 is given by 2, 1. The metric space E1D is complete, separable, and locally compact, and the following properties for the metric D are valid. Note that this metric space E1D is linear normed space with this norm. Let U in E1, we denote U alpha, the alpha cut of U. Then we have the left hand and right hand endpoint of U alpha are continuous and monotone increasing for left hand endpoint and monotone decreasing for right hand endpoint of U alpha. Another definition, the generality, the Hikuhara difference of two fuzzy numbers U and V in E1 is defined as follows. Let's move to the first subsection in which we will talk about the fuzzy fractional derivative. So the first the definition, let x0 in AB and h be such that x0 plus h is in AB, then the generalized Hikuhara derivative of fuzzy value function f at x0 is defined as follows, is given by the formula 2, 3. Another definition, let f defined in 0 in interval EB into E1 and x0 is in EB with the left and right hand endpoint of alpha cut of f both differentiable at x0. So we see that f is a differentiable at x0 if we have the formula 2, 4 and f is doubly differentiable if we have the formula 2, 5. In the same way, we say that f prime is E differentiable if we have the formula 2, 6, and we say that if prime is doubly E differentiable if we have the formula 2, 7. Another theorem, let f function and g two differentiable function, then we have the formula 2, 8. Let's move to the second subsection in which we will talk about generalized fuzzy fractional derivative and their property. So let f fuzzy function, then then the fuzzy Riemann-Liouville integral of f is defined as follows. By using the alpha cut of function f, we can define the fuzzy Riemann-Liouville derivative of f. This derivative is given by the formula 2, 10. Also, we see that f is E differentiable if the derivative of f given by 2, 11, and f is double E differentiable if we have the formula 2, 12. Let f fuzzy function, then we have the following two property which will be used in the proof of our result. Let's move to on the last section in which we will discuss the problem given by 3.1 where f is a fuzzy continuous mapping and gamma in 1, 2. So we consider the following equation where the g is the grain function given by the formula 3, 3. Then our result is given by this theorem. So we suppose that f is continuous such that the left and the right hand endpoints of alpha cut of f are continuous function with respect to alpha, and there exists a function m such that we have this two inequality. Then x is a solution of equation 3.1 if and only if x is a solution of equation 3.2. For proof, we will start with the first sense. So let x be a solution of 3.1. Then by using the formula 214, theorem 1 and proposition 2, we can see that x is continuously derivable and verify the equation 3.2. On the other hand, for the other sense, we will suppose that x is a solution of 3.2 then we replace omega by its expression. So according to theorem 1, we have x belongs to E1, and by using the following property, we get that x is a solution of tree 1. As remarked, in the same way and same condition, we can prove that the problem tree 4 is equivalent to the equation given by tree 5. Let's move on the second result in our work. So let f a fuzzy continuous function satisfy the condition of the last theorem, and we have inequality 3,6. Then the problem 3,1 has a unique solution. For the proof, consider the following mapping given by 3,7. Since f is well defined and the space E1D is a complete metric space and the interval 0a is a compact of R, then the space is a complete metric space. And since f is a contraction mapping, then by fixed point theorem of Banach, f has a unique fixed point, which is a solution of tree 1. And thank you for your attention.
Hello, my name is Dimple Khalvazi, and today I'm gonna present our work, which is based on the simulation of COVID-19 epidemic spread using stochastic differential equations with a jump diffusion for SIR model. The plan of our presentation is as follows. First of all, we are going to give an introduction and motivation of this work. Then we are going to present the methods that we used in order to simulate or to modelize the spread infected infected cases of coronavirus, which are the stochastic differential equations with the jump diffusion, and based on the SIR model under this stochastic environment. After that, we are going to present the parameter estimation, and then numerical simulations, and finally we are going to give a conclusion and some perspectives. So first, the introduction and motivation. As we know that the epidemiology is the study of the spread of disease with the objective to trace factors that are responsible for or contribute to their concurrence. And the objective of this modelization is to evaluate strategies in order to control and spread of a disease or a virus, for example, the new coronavirus. This novel coronavirus has caused a large-scale infection in the whole world since its appearance for the first time in Wuhan, China. This had led to a significant impact on the lives and economical world. The rapid growth of this COVID-19 has obliged the mathematical community to analyze and propose models in order to reduce the negative consequences of this epidemic and then accelerate the recovery phase. So we can see that the mathematical model of infectious disease is central in epidemiology and may play an important role in predict and estimate disease transmission, recovery, death, and other significant parameters. So here we are going to give three categories of mathematical modeling of infectious disease dynamics. First, the statistical-based method for epidemic, which is, for example, regression techniques, spatial models, statistical processes, also the autoregressive models. We have also the mathematical state space models, like deterministic SIR model, Markov chain model, stochastic model, etc. And also we have the empirical or machine learning based model, like neural network, machine learning, web-based, or our choice was to use a SIR model, classical SIR model, but this time we are going to put it in a stochastic environment. So first we are going to introduce the SIR model. SIR model, as we know, is one of the powerful models that can be used to mathematically model infectious disease. Here we have three equations which represent the SIR model, with S is the number of individuals susceptible to be infected at time t, I is the number of infected individuals at time t, R is the number of recovered persons at time t, even by recovery or death, and the parameter beta and gamma are the infectious rate and the removal or recovery rate. So we can see here that SIR is one of the simplest and powerful models intended to model infectious disease and to study the means by which disease spread, to evaluate strategies that can control the pandemic. But our goal here is to put this classical model and combine it or put it in a stochastic environment. For this reason, we are going first to present the stochastic differential equation with jump diffusion. A stochastic differential equation serves as a mathematical model for systems involving two types of forces. One is determinist and the other one is random. In general, a stochastic differential equation is given as the equation dxt equal a function multiplied by dt and another function multiplied by the geometric or the Brownian motion. And as a solution of this equation, we have the integral equation xt, which equal to x0 plus the integral of f plus the integral of g multiplied by the Brownian motion. Here we can see that this is the if we put this Brownian motion, or if we consider this Brownian motion as a geometric Brownian motion, we are going to be in the case of a Black-Scholes model. This Black-Scholes model is one of the most popular and important model used in finance or in finance. So the idea here is to we adapt the Black-Scholes model to an epidemiological mathematical model. We do know the importance and the good result that Black-Scholes give in the financial market. Our objective here is to see if this model can give the same or the same important and good results in epidemiological fields. So our SDE become the equation 4 with mu and is the drift and sigma is the variance, and the solution is now the solution of the Black-Scholes model is in the equation 5. So our analysis of COVID-19 spread is based on a stochastic differential equation, but this time with jump diffusion. So we are going to add to our stochastic differential equation another process which present the compound Poissonian lambda. Then we can write our SDE with compound Poissonian jump as follow the equation 6, with the xt means the left limit of xt. And the solution of this equation is also known, which is equal to equation 7. Now we are going to put our SIR model that we have already present at the introduction. We are going to put it under a stochastic environment with jumps. So we transform the deterministic SIR model into a corresponding stochastic problem with the jump diffusion. So we assume that the beta and gamma are constant, so the expected value of the total population is constant and equal to n. We can also see that the derivative of s plus the derivative of I plus the derivative of. We suppose that the infected cases takes place continuously on the time interval t. So a standard Brownian motion is defined here with a natural filtration. So now we get a new system of equation of SIR model, which is a stochastic now SIR model with the jumps. So each equation we add to it a random variable or a Brownian motion, geometric Brownian motion, and we add to it also jump processes or jump diffusion, a jump process which is Poissonian jump processes. With the sigma is a constant, and as we said, the W is the Brownian motion, G is the compound Poisson processes. Here, with no loss of generation, we will focus on the infectious cases for the first stage, and we can generate the same processes and methodology for the other parameter or for the other susceptible and recovered cases. So initially, in the absence of infections, we have I plus R equals 0, and according to the equation 1, we obtain the following relation, which is expressed in equation 9. So adding this equation 9 and 10, we can get finally the new equation of. Now we are going to next point in our presentation, which is the parameter estimation. Since the traditional deterministic SIR model has two parameters, the infection rate and the recovery rate. So these parameters can be estimated as follow using the equation 12 and 13. We can get these two parameters, and then in order to find the volatility or the variance of our stochastic differential equation, we can use the equation 14 and 15, and then using the Monte Carlo simulation, we can find the close rate in order to implement our jump diffusion model. So here, after finding the three parameters, the gamma and beta and sigma, or sigma, which is equal to alpha multiplied by I, when we find these three parameters, we can solve our stochastic differential equation easily, and then we can have now the numerical simulations. So we analyze and predict the trend of COVID-19 by using our stochastic SIR model, which jumps presented previously. And for our prediction of infected cases of COVID-19, we use the data obtained from Johns Hopkins University Center for System Science and Engineering, and we collect the number of daily reported confirmed cases for the COVID-19 epidemic in Morocco from March to July. And we have three steps that we follow. First, we given the historical data from a certain period. Then we measuring the corresponding beta and the gamma and sigma by using equation 12, 13, 14. Then we solve the system of the stochastic differential equation with the jump of the infected cases. Here we present the real data set of Morocco in this period of March to July. And then we present here the jump diffusion or the result obtained by our new model or the jump diffusion model. We based on the deterministic SIR model to estimate different parameters related to the COVID-19. Then we try to develop the classic SIR model by adding a stochastic variation. This combination gives us these results. In comparing the real data with the data obtained stochastic differential jump diffusion model, we can see that stochastic modeling can give approximate results close to reality. Otherwise, the study shows that geometric Brownian motion with jumps can predict perfectly the future without needing a large data sets. And that leads us to see that to say that the Black-Scholes model is also have a good result in this field too. As a conclusion and perspective, we can see that SIR model is one of the traditional methods to see the behavior of the pandemic with easy computation, but doesn't give a real closed result to the reality. So if we add the stochastic variation, we can get more satisfaction results. So this is the ER very popular in many fields such as finance. As we said, the black shows the importance or shows a very big role in finance, and we prove that it can be used also in other fields, not just finance. And this new approach proves the reliability and its performance since the results are satisfying and close to reality. As a perspective, we can extend our work and generate the simulation for the other equations of SIR model by doing the same processes, repeating the same processes, and also we can get more satisfaction results if we take a large data, or if we work in a large interval of time. Thank you so much.